let us discuss today the properties of estimates for large sample. So the properties of goodness of fit is the application of its properties for large samples. When sample size is very large, say to n tends to infinity, then we can obtain goodness of fit. Now, this is called the asymptotic properties. Now, what are those asymptotic properties? That it is asymptotic unbiasedness. There should not be bias between the estimates and the population parameter. Okay, difference should be small or nil. Then consistency and asymptotic efficiency. So sample size are successively increasing. Suppose first sample, suppose N1, and second sample is N2. So N2 should be greater than N1. That means N1 is less than N2, then N2 is less than N3, and so on. So successively, the sample size should be increasing. Suppose let beta the estimate of parent population. So the parent population estimate is beta, and estimated beta for N1 sample, then beta for N2 sample, it is not minus, sorry, and this is N2. And so on, and beta for NT for N number and T samples. So estimates of each sample size, then sample distribution, what is expected beta and variance of beta. So expected beta of the estimate is expected beta, and variance is expected beta minus see estimated beta minus expected beta. So expectation of the difference square. So this is the variance. Then sample will be repeated for successive increasing size. It is called asymptotic distribution or limiting distribution of the sequence xn. So next is asymptotic expectation. Now let the sequence of random variable is xn is equal to xn1, then xn2, so on up to xnt. So out of n there are nt number of sequences. So sequence of expected values. Sequence of expected values will be simply expected x1, xn is equal to expected xn1, expected xn2, and so on to expected as nt. Now, when n tends to infinity, suppose n is very, very large, we have already discussed for small sample, and this is for a large sample. So when sample size is very large, to infinity, then expected values converts to a finite constant mu. So the expected values for a large number of n we will converge to a finite constant, mu. And mu is known as asymptotic mean of the sequence xn. And what is mu? It is called the asymptotic mean of the sequence xn. Now it is also the limit of the sequence of the expectation. It is expressed as, so asymptotic expectation of xn. How it is expressed? This is limit when n tends to infinity. So expected xn is equal to mu. So this expressed like this. Now asymptotic variance. Now our sequence is this, as we have written earlier, that sequence of xn is equal to xn1, xn2, and so on up to xnt. And asymptotic expectation is limited. Limit n tends to infinity, and expected xn is equal to mu. Okay. Now the sequence of variance of the individual distribution is. Now what will be the sequence of variance? Expected xn minus expected, that is first expectation of the whole thing. That means xn minus expected xn square. What result you will get, it is the expected. Okay, that is the expected values. So it is, this is equal to xn1 minus expected values of xn1 square, then what value will get, expectation of that, comma. So next is same thing, that xn2 minus expected xn2 square and expectation of that, and so on, will go up to xn. So when n tends to infinity, in many cases the limiting value is 0 and the distribution is degenerate. So when limiting value will be 0, then we say that the distribution is degenerate, because when n is very, very large, it may so happen that in some values, that is variables, within n, the limiting value may be 0. Not all zeros, but some may be zeros, because n is very large. So in that case, the distribution is degenerate. It needs a new sequence of variance, and the expected value of the deviation is multiplied by root n. So sample size n, it is multiplied by the sample size. That means the expected value of the deviation is multiplied by root n. So if it is the case of degenerate, so if we multiply by n, then new sequence will be this one. So and then we get expectation of this. Now we have multiplied by root n. So this will be distributed as, suppose there are n number of samples, then for n1, simply it will be n1, n1, n1. So for n1 it is expected values of n1 multiplied by this variance. Then secondly for n2, thirdly next will be for n3 and so on up to nt. So if n tends to infinity, suppose n is very very large, then new sequence will converge to a finite constant. That means limit of this multiplied by root n, xn minus expected xn square, and the variance multiplied by this root n will be a finite, will be equal to a finite constant. In this case, the variance of the asymptotic distribution of the initial sequence is defined as. So in this case, what will be the variance of the asymptotic distribution? So variance will be xn is equal to 1 by n into b. Now taking limit, so taking limit 1 by n limit of this variance when n tends to infinity, so this xn minus estimated xn n square. So expectation of the whole thing is multiplied by 1 by n, taking its limit will be the variance of the asymptotic distribution. So for further details, one can see the book on econometrics by H. Tay, The Principles of Econometrics by North Holland, 1971. It is in page number 377 to 8. So, next properties we'll discuss. Thank you for watching and keep on watching.